To finish this section, and it is a very short section, we're going to look at a couple more examples here. The first one says use the graphs of x equals f of t and y equals g of t to sketch the corresponding parametric curve in the xy plane. Now, x is represented by this graph here on the left. So this is a straight line. The slope is -1. It goes down 1 over 1. And the y-intercept is 1. So I could represent x by this. Oops. F of t is equal to -t plus 1. So x equals -t plus 1. And I can then rearrange this. If I bring the t to the left and bring the x to the right, I end up with t equals 1 minus x. Now I'm going to do the same thing here for the second curve. So the y equals g of t curve, you can see that this is a parabola, and the parabola has been flipped upside down, and it's been raised, because normally the parabola starts here at the origin. So this parabola, which is g of t, would be given as -t squared plus 1. So that negative is going to flip it upside down. The plus 1 moves it up 1. So we have y equals -t squared plus 1. So now I can substitute that t into here if I want to get just one Cartesian equation. So we would have something like this. Y equals -1 minus x squared plus 1. That would be the Cartesian equation. And to be honest, that may or may not be easier for you to graph, depending on how comfortable you are with function transformations. This is a parabola that's shifted over, shifted up, and it's got a couple reflections happening. If that's not something that you're terribly comfortable with, don't worry about it, because you could also sketch it using its parametric equations, okay? And I'm going to show you that you could do that. I'm going to make use of x is -t plus 1 and y is -t squared plus 1. And I'll do a couple points and you'll kind of see where it's going. If we look at time 0, so t is 0, the x value would be 1, and the y value is also going to be 1. So at time 0, we have the point 1, 1. So that's here. So let's look at time of 1, the t value being 1. So x is -1 plus 1, so x would be 0. Y would be -1 squared, so that's -1 plus 1, so y would be 0. So we have this point. Let's look at time 2. So if time t is 2, we have -2 plus 1 for x, so our x value is -1. The y value is going to be -2 squared plus 1, so -4 plus 1, or -3. So when t is 2, we've got -1, -3. And this is going to continue down. So this is going to be the parabola, so you can see it's going to continue down. Well, what happens the other way? So what if we look at some negative values for t? So we started, this was time 0. It was this top point here. So what if I look at time as -1? If t is -1, I have the opposite of -1, or +1 plus 1. So x would be 2. Y, if t is -1, t squared is +1. -1 plus 1 is 0. So I get the point 2, 0. And you could continue this, and you'd get the other side of the parabola. So in this case, even though I'm going to draw it from left to right, it's not a pretty drawing, but I'm sorry. The path of travel for time actually would go, in this case, from right to left. And again, if you wanted to graph it just from this equation down here, you will get the exact same graph. Now, the last example I want to look at here, it says find parametric equations and a parameter interval for the motion of a particle that starts at a0 and traces the circle x squared plus y squared equals a squared. So from a previous example, we made use of the identity that cosine squared plus sine squared equals 1. So what I'm going to do is I'm going to attach some a's to that. I'm going to say that a squared cosine squared, we'll give it a t, plus a squared sine squared is equal to a squared. So it's just taking the identity of cosine squared plus sine squared equals 1 and multiplying by a squared to all the terms. Well, that can work here because that gives me x as being a cosine t and y a sine t. Okay? So we're just going to define x and y in terms of a times cosine t, a times sine t. Now, we've got a circle. We don't know our value of a, but we know that we've got a circle of some sort. I'm just going to draw a circle with a radius of 2 here. But that's just arbitrary. A could be anything. So you could have a circle of any size. It could be really big. That's fine. I'm actually going to start with a B here because it says once counterclockwise. And the way angles are defined, they're defined in a counterclockwise motion. So the x-axis is defined as 0. And then as we move counterclockwise, our angles get larger and larger. We go up to pi over 2, then we go to pi, then we go to 3 pi over 2, and then finally we end up back at the x-axis with 2 pi. That's how angles are defined. So in that manner, the parameter interval is going to go from 0 to 2 pi to make a complete circle. So I'll go ahead and write that down. And our values for x and y can just be as I mentioned before. So x would be a cosine t, and y is a sine t. So at point A, okay, our starting point, cosine of 0 is 1, so the x value is a. Sine of 0 is 0, the y value is 0, so it would be the point A0. And again, we'd end up back there. If I were to jump down to part D, it says do it twice counterclockwise. Well, the equations for x and y aren't going to change, but instead of stopping at 2 pi, we're going to go around a complete circle again. So that means I'm going to go all the way up to 4 pi. So let me go ahead and write down what we have here. So that's the only thing that's going to change. Now, the two that I skipped, though, are going clockwise. So, like I said before, normally our angles are going to go in a counterclockwise manner. But what if we want our circle to go clockwise? So it's going to go opposite to what we're used to. A full circle is still going to go from 0 to 2 pi, but we do need to make a slight change. So for once clockwise, our t values are still going to go from 0 to 2 pi. But instead of my y values, so when I'm dealing with, let's say, t equals pi over 4, so that would be the point approximately right here, okay? If I'm looking at t is pi over 4, and I'm using the equation that I have, for instance, in part B, it's going to give me a y value up here, but I'm going clockwise now, so I want that y value to be down here. So I want the y value to be opposite of what it is. So what I'm going to do here is I'll define x the same, but y just needs to be the opposite of what it was defined as before. So that means when I'm up here, it's going to give me points in the fourth quadrant, okay? So as the angle moves into the second quadrant, the y values will be bumped down here. So it's going to allow this circle to be drawn in a clockwise manner. So again, it's going to start here and end right here on the x-axis. But by making those y values negative, we're going to be able to draw it in that clockwise fashion. So for part C, I will use the same thing as part A. So x is a cosine t, and y is negative a sine t. But since this one is twice around, just like I did it with the counterclockwise, t will go between 0 and 4 pi.